This is lecture 19, and these are some problems finding maximums and minimums, at least beginning problems. So in the first set of problems, you were supposed to sketch a graph by hand using some knowledge of elementary functions, and then to look at what the absolute max and min were. So I just want to do one of those. This is number 25. So the function that we're looking at is f of x equals 1 minus the square root of x. Okay, to draw the graph of this without working very hard, you need to start with the graph of the square root function, which you really should know. It's this half parabola. It grows like that. So this is the square root of x. Now, if you negate it, of course, that's going to make it flip down to there. So this graph would be the negative of the square root of x. And 1 minus that would mean this thing, add 1 to it. So everything here gets shifted up 1 unit. So this point at 0, 0 would end up at 0, 1. And then the curve would go down from there. So it's going to have a vertical tangent line, and then it's going to go like that. So that's the graph of 1 minus the square root of x. And the question is, find the absolute and local maxes and mins for this function. Well, there isn't going to be any min. This function just keeps going down, 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 down. For every x value, there's a y value that's, as you move to the right, it'll be lower. Not by much, but it will be. And then this point right here is as big as it gets, and this is the point 0, 1, which you can see if you plug 0 in here, you get 1 for y. So that's all there is to it. And all of those problems at the beginning were pretty much like that. Let's do 28 because that one is a piecewise defined function. So the graph or the function definition for problem 28 is this messy looking thing. 4 minus x squared or 2x minus 1. So it's 4 minus x squared if x is between -2 and 0. So -2 less than or equal to x less than 0. And then from 0 to 2 inclusive, we have this. So the domain of this function, I can plug in any number from -2 all the way to 2. See, any x, including 0. If I plug in 0, I have to use this formula for the definition. Okay, so what is the graph of this mess going to look like? And it's not that bad. What we have to do is take each piece separately, restrict its domain, and then think about it, and then put them together. Okay, so what's 4 minus x squared? Well, x squared you all know. Minus x squared would be just the flip, turning it upside down like that, and 4 minus it would be adding 4 to it. So you take this vertex and move it up to 4, and then draw this downward parabola, and that's the graph of 4 minus x squared. Except for one thing, we're only looking at it from -2 to 0. So where's -2 on this? If you plug in x equals -2, you get 4 minus 4 is 0. So just as luck would have it, that's the point -2. So we're only looking at this part of the curve from -2 to 0 and not including this point. So let me see if I can find my eraser here. So what I'm going to do is erase all of this part right over here. And I'm going to erase all of this part because it doesn't belong either. And I'm going to erase that point there. Okay? So that's going to take us back to a hole there. And that's this part of the curve from -2 to 0. All right? Now, what's 2x minus 1? You all should know that instantly. That's a line of slope 2, y-intercept -1. So if I write a line of slope 2, y-intercept -1, here's -1, and at 0, that's where we're going to be, at -1. So I have a hole here, and I have a line of slope 2. So it's going to go up like this. But it's not that forever. It's only from 0 to 2. So if this is the point 2, then I've gone far enough. So this is minus 2, and this is 2. Well, it doesn't look real even, does it? Well, we'll cut it back. This is 2 right here then. So none of this stuff counts. I'll just draw a big dot on the end. How's that? Anyway, the whole idea is, what is that y value, by the way? Maybe I should be a little bit more careful. What is the y value when x is 2? This would be 2 times 2 is 4 minus 1 is 3. So this would be 3. So I've not done a really good job of drawing this. Time to get the eraser back out. So really, the y value up here is 3. Okay, so let's fix this up. So at 2, the y value is going to be 3. Let's check that again. 2 times 2 is 4, minus 1 is 3. So when x equals 2, that's the formula that we have to use, and so it's going to connect up here. So the graph is going to be a straight line like that. Okay, and this point is at 4, because when x is 0, y is going to be 4. Okay, so what's going on with this function? This is a very interesting function. The question is, what are the maxes and what are the mins? Where are the extreme values? And let's just review. Make sure you understood what I did here with drawing the picture. I drew the line 2x minus 1. It's a line of slope 2, y-intercept 1. And I just cut it off on the negative part, anything less than 0, because that's the domain. And I cut it off at 2. And I had to figure out where that point was, so I plugged 2 in. And then I compared that, or glued it together with this curve. And you see it's discontinuous, right? But that's the way it is. Life is like that sometimes. Okay, the question is, what are the maxes and mins? Well, is there an absolute max to this function? If there were an absolute max, it'd be this point right here, but this point is not included. And this part of the curve just keeps getting bigger and bigger and bigger, getting closer and closer to 4, but never equal to 4. So there is no absolute max for this function. And it's evident that there is an absolute min, this point right here, where x equals 0 and you get y equals minus 1. So at 0 minus 1, we have an absolute min. Now you can say it the way I just did it here, or you can say simply x equals 0 is the absolute min. Okay? Now there are all kinds of other mins. There's a relative min at x equals negative 2, and there's a relative max at x equal to 2. Those are endpoint minimum and maximum. Okay? And at this point, there's just nothing. There is no maximum value here. And this point down here is the absolute min. It's also a relative min, if you wanted to count it. All right? So much for that. Okay, the next problems in 29 to 44 say to find the critical numbers. So I've picked a few of these to do, and these are all pretty much crank and grind problems. So let's start with 31. 2x cubed, so the question is find the critical numbers where y equals 2x cubed minus 3x squared minus 36x. So the derivative of that is pretty simple. Y prime equals 6x squared minus 6x minus 36. A lot of 6's here. Why don't I factor those out so I know what I'm looking at better. 6 times x squared minus x minus 6. Okay, that's the derivative. The derivative, we want to know where is the derivative equal to 0 and where is the derivative undefined. Well, obviously the derivative is defined everywhere, so that's not going to be no critical numbers from there. But I can factor this, I bet. I bet this factors, yeah, x minus 3, x plus 2. So if I can factor it, I do that, and then I can tell instantly that x equals 3 or x equals negative 2. Those are critical numbers, or critical points. Okay, that's it for number 31. Let's take a look at number 38. 38 says x to the 1/3 minus x to the negative 2/3. So this is our function, or I guess they called it g of x. Okay, so g prime at x is going to be 1/3 x to the negative 2/3, right? 1/3 minus 1 is negative 2/3. And then the derivative here is going to be minus 2/3 times minus 1, which is plus 2/3 times x to the minus 2/3 minus 1, which is going to be minus 5/3. Right? Now we need to analyze where is this undefined and where is this equal to 0. Well, the first thing is that this will be undefined where x equals 0, obviously, but I can't plug 0 in here either. I can plug 0 in here. The cube root of 0 is 0, but the cube root to the negative 2/3 means 1 over x to the negative 2/3, or 0 to the negative 2/3 would mean 1 over 0 to the 2/3, and 0 to the 2/3 is 0, so that would give you 1 over 0. This is undefined. So 0 is not in the domain here. So the domain, these are cube roots, so that's not a problem with negative numbers, but the domain would mean all numbers other than 0. Here the derivative only blows up at 0. We can't put 0 here, we can't put 0 here because of the negative exponent, because this means 1 over whatever. Okay, so the critical numbers of the second type, there aren't any of those. But we can set this equal to 0 and solve. And the first thing I would do is multiply both sides by 3. And then I'd rewrite these things as fractions to try to get a common denominator. So multiplying by 3 gets rid of this entirely and leaves me with 1 over x to the 2/3 plus multiplying this by 3 gets me a 2, and then this is divided by x to the minus 5, or to the plus 5/3, sorry, x to the plus 5/3. Okay, now I said I need a common denominator, but yeah, that's going to be a mess, isn't it? We want to see where is this going to be a common denominator. I think I would like to get out of these fractions. So let's see if we can multiply by, well, no, let's just do it without thinking too much. Cross multiply this thing out. So we're going to have x to the 5/3 plus 2x to the 2/3 on the top. And then on the bottom, the common denominator, well, no common denominator, it's the product of the two. X to the 2/3 times x to the 5/3. So this has to be equal to 0. Now, I'm not even going to bother to simplify that denominator, simply because I've got a fraction here, which is equal to 0. How can that be? The only way is for the numerator to be equal to 0. So that gets me x to the 5/3 plus 2x to the 2/3 equals 0. Now, I'd really like to factor. How about if I factored, can I do this? X to the 1/3, factor an x to the 1/3 out of that. What would that leave me with? X to the 1/3 times x to the 4/3? That doesn't seem to be too productive, does it? Can I factor? No, maybe I got a better idea. See, we're fishing around for things to do to simplify this thing, to make it something that we can recognize. What if I multiply both sides by x to the 1/3? I think that's going to make it look nice. Multiply both sides by x to the 1/3. On the right, of course, you get 0. But on the left, when you distribute this guy across the sum, x to the 1/3 times x to the 5/3 gives you x to the 6/3. Isn't that nice? X to the 6/3 is x squared. And then x to the 1/3 times x to the 2/3 is x to the 3/3, which is just x. This is looking good. So that says x times x plus 2 equals 0. And now we're done because x equals 0 or x equals -2. Oops, we're not quite done. Something bothers me. What about this guy? Seems to me that I remember somewhere that I'm not allowed to have 0, right? Isn't that what this says up here? X not equal to 0? Because I can't plug it in here. So this is not a critical number. We got to cross that one out. So really, in this problem, there's only one critical number. That's that one. Okay? So, kind of a tricky problem. All right, let's do number 40. This doesn't look like much fun either. It's a trig problem, or it's got a trig function in it. Number 40 is g of theta is 4 theta minus tangent theta. G of theta is 4 theta minus tangent theta. Okay, so the domain of this is, well, you got to not allow tangent to blow up, and the tangent will blow up wherever cosine is 0. So there's lots of places here where this thing blows up. We'll have to come back and remember that. I don't feel like writing all that out. So let's go ahead and just calculate the derivative. The derivative is the derivative of a difference, so I take the derivative of each part and subtract. Derivative of 4 theta with respect to theta is 4. Now the derivative of tangent, you have to remember, is secant squared. So this is the derivative. Now, what about where this blows up? The secant is 1 over the cosine. So this is going to blow up exactly where this one blows up. So there's no critical points of the second type here. Because every time you would get this to blow up, you would also get this to blow up. Because here's what I'm thinking. Tangent is sine over cosine, and secant is 1 over cosine. So if this blows up because the cosine blew up, the cosine is 0 rather, then this is going to blow up because the cosine will be 0. See? Okay, so this derivative will never be undefined, but I can make it equal to 0, and that just says 4 equals secant squared of theta. So now I'm going to be a little bit careful. How can the secant squared be equal to 4? Let's break that into sines and cosines. That would be 1 over cosine squared theta. So if I multiply this out, that would say cosine squared theta equals 1/4. So cosine of theta would have to be plus or minus 1/2. I said I'm being a little bit careful here. Remember, the square root, there's 2 possible ways of getting to 1/4. Okay, so when is the cosine equal to plus or minus 1/2? Well, we got to think about the unit circle again. So on the unit circle, the cosine will be 1/2 here, where the angle is pi over 3, a third of the way, because the cosine will be the short side of that 30-60 triangle that you get there. So pi over 3, also minus pi over 3, because at minus pi over 3 we're down here. Cosine's exactly the same thing. But you know, we got minus 1/2. That's going to happen over on this side. So at 2 pi over 3, we're going to have a negative 1/2 for the cosine. And at 2, 3, 4 pi over 3, we're going to have another negative 1/2. So it looks like 1 pi over 2, 1 pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. So there's just an awful lot of these. Minus 3 pi, no, not minus 3, minus 2 pi over 3, minus 4 pi over 3, and so on. The next one, let's see, let's go this way. If we count pi over 3, 2 pi over 3, 4, 5 pi over 3, the next one is going to be 7 pi over 3, 9 pi over 3. So there's a way to write all of that, but at this point it's not worth writing all of them. You can just say etc. So those are the places where the derivative is equal to 0. Okay, because that will make, did I do that right? I'm sorry, I did that exactly wrong. Those are the places where the cosine squared, no, that's right, cosine squared is equal to 1/4. I did not solve for cosine equal to 0. I thought I'd done that. No. So this is right. All of these numbers plus any, I guess the right way to do it is any of these numbers, pi over 3, 2 pi over 3, minus pi over 3, let's see, pi over 3, 2 pi over 3, minus pi over 3, and minus 2 pi over 3. I didn't have that written anywhere. Yeah, there it is. All of those numbers plus any multiple of 2 pi, n times 2 pi. So if you add n2 pi to any of these things, you'll get another place, exactly the same place on the unit circle. So those are all of the places where the cosine theta is plus or minus a half, and all of those places will make the derivative equal to 0. Okay, you can see that these are nasty only in terms of the algebra and the derivatives, but the idea should be fairly simple. You want to find the places where the derivative is 0 or the derivative is undefined. And for derivative being undefined, it had to be a place where the point was in the domain of the function in the first place. Okay, how about number 42, 3t minus arcsine t. 3t minus, I'll write it this way, inverse sine t. So this is our function f of, h of t, sorry. So this is our h of t, and we want the critical numbers. Now, inverse sine is this nasty function that has a graph that looks something like this, if I remember correctly. So, what are we going to get for the derivative of this thing? H prime of t. Well, the derivative of 3t is easy. That's 3. And then you got to remember the derivative of the inverse sine. And I do remember it. It's, I think, 1 over the square root of 1 minus t squared. All right, so this is the derivative. Where is this thing going to blow up? You know, one of the things that we need to do is to figure out what the inverse sine's domain is, because I never bothered to do that. I need to know what the domain of this function is. And the problem is not with 3t, the problem is with this guy. I can't plug everything into the inverse sine. Okay, so let's do this review how we got the inverse sine in the first place. We got the inverse sine by trying to construct an inverse for this sine function. And the problem is that to find the inverse, it's not 1-to-1. So eventually, as you go around here, you'll see that you get the same y value like here and here. And that's no good for an inverse, because for an inverse, you can't tell which x value this y value came from. So we end up just restricting the domain of the sine. We stop here because we'd start getting duplicates. So none of this stuff out here would be counted. And then we'd have to stop here and throw away all of this stuff. So the domain of the sine gets restricted to just from minus pi over 2 to pi over 2. Now those are the x values for the sine that give us y values from minus 1 to 1. The inverse sine, on the other hand, will take x values that go from -1 to 1 and give us y values that go from minus pi over 2 to plus pi over 2. So they go backwards. The inverse sine is going to go backwards. So it starts with these numbers that we could possibly get. So we can't take the inverse sine of anything that is bigger than 1 or less than -1. Those are the biggest that we can get here for y values. So those are the biggest that you can plug in here for x values. So the domain of this function is already just this interval. All right, what do we get when we take this derivative? Well, when is this going to not exist? This is going to not exist when the denominator is equal to 0 or when this stuff under the radical is negative. Okay, what does it take to make this equal to 0? That's pretty easy. 1 has to be equal to t squared. That means t has to be equal to plus or minus 1. Well, now, here's the problem. This is the first time that we see that if t is equal to 1 or -1, we're going to make this derivative blow up. But this function has a perfectly good value. If t is -1, for example, what is the inverse sign of -1? Well, the answer is minus pi over 2, because the sign of pi over 2 gives us -1. That's not a problem. So at -1, this number here, sine inverse of -1, is minus pi over 2. And then you'd have to take 3 times -1 and tack that on, and that's the value of the function at that point. Similarly, when t equals 1, inverse sine of 1 would be the angle whose sine is 1. That would be pi over 2. So this number would then turn into pi over 2. So at both 1 and -1, we can plug those into the original function. So let me summarize that. H of 1 and h of -1 are okay. There's nothing wrong with that. There's perfectly good y values. But h prime, because this is the domain right here for the original function h. Right? So the domain is that guy. But when you look at the derivative, t is not allowed to be equal to plus or minus 1, because otherwise the derivative would blow up. So guess what, folks? This is the first time that we're seeing a case where we have values that make the derivative blow up, but not the original function. So these two numbers are critical numbers. They're critical numbers of the second type, places where the derivative does not exist. Another way to make this thing not exist is to put a t value that would make the radical a negative number under the radical. And that would mean that t would have to be bigger than 1 when you square it. But the only way to have that happen is for t to be bigger than 1, and you can't have t bigger than 1 either on this end or less than -1. So there's no way to make that radical under the radical negative. So that's about it. This is the only way to make the derivative not exist. So another way to say that is at t equals plus or minus 1, h prime at t does not exist. And so these are critical numbers. Okay, I still have to figure out critical numbers of the first type. That would be where the derivative is equal to 0. So if I set this equal to 0, I need to solve the equation 3 minus that thing equals 0. So that would mean 3 equals that thing. So if I multiply both sides by the denominator and move the 3 to the other side, I get the square root of 1 minus t squared equals 1/3. Now I can square both sides and get 1 minus t squared equals 1/9. Switch the sides again, so move 1/9 to the left and t squared to the right. So we're going to get 1 minus 1/9, which is 8/9, equals t squared. So t is going to be equal to plus or minus the square root of 8/9. And that's good enough because the question only asked what are the critical numbers. Okay, let's take a look at another couple of problems. Now we have to find the absolute max and min for a function on an interval. So that takes us to, let's try problem number 50. Sorry. So problem number 50 says we got this function, f of x equals x cubed minus 6x plus 5. Get that right? X cubed minus 6x squared plus 5. And this is on the interval from -3 to 5. Okay, so now our problem is fully complex. We want to find the absolute max and the absolute min. So where is the absolute max and the absolute min going to be? It's going to be at either a critical number or at an endpoint of the domain. So as a good detective, these two guys are immediately suspects. The absolute max or min can happen there. But also the absolute max and min can happen where the derivative is undefined, does not exist, or equal to 0. Well, obviously the derivative is going to exist everywhere. 3x squared minus 12x is going to exist everywhere. I'm going to factor the 3x out of it and leave me with x minus 4 and set that equal to 0, and then I can tell that when x equals 0 or x equals 4, those are two more suspects. This could be, this could be, this could be, or this could be. So I've got 4 numbers to tell. How can I tell what the absolute max and absolute min are? I could graph this thing, I suppose, if I really wanted to work hard. But the easy way is to just take every one of these critical numbers or endpoints and plug them in and see what you get. One of these guys has to be the absolute max and one of these guys has to be the absolute min. There are no other critical numbers. So you just calculate f of 0, that would be 5. F of 4, that would be 4 cubed minus 6 times 4 squared, which is 16, plus 5. Might have to use a calculator one of these times. 4 cubed is 64, and 6 times 16, I don't know, 96, and then add 5, so whatever that is. 96, 64, what is that, 20, 30, negative 32 plus 5 is minus 27, if I did my arithmetic correctly. And we got to plug in the endpoints too. Got to plug in negative 3, and you get negative 3 cubed, which is minus 27. I can do that. And then minus 6 times negative 3 squared, which is 9, plus 5. So this is going to be minus 27 minus 54. Yuck. 54. That's going to give me 81. Minus 81. Minus 81 plus 5 is minus 76. So this is even smaller than that one. And then finally we got to plug in 5. F of 5 is 5 cubed minus 6 times 5 squared, 6 times 25, plus 5. And what is that? This is 125 minus 6 times 25. That would be 150, I think, plus 5. And that's going to be minus 25 plus 5 is minus 20. Okay, you can see why I'm not a big fan of these problems, a lot of arithmetic. But now you just compare these answers. Minus 76 is obviously the most negative of all of these. So this is the winner. Negative 3 is the min, and this is an absolute min. There is no smaller point than at negative 3. All right. And then at 5, well, where's the other one? What is the biggest that this thing gets? Looks like the biggest that this thing gets is at 0. So 5 is going to be our other, no, sorry, 0 is going to be our absolute max. Okay, so our conclusion is that this is the absolute min, this is the absolute, and at negative 3, at x equal to negative 3. And at x equal to 0, we have our absolute max. Now, I'd really like to check that. Now, how am I going to do that? Well, one way to do that is to crank up Maple and ask for Maple to graph this thing for us and see what it's going to look like. And maybe we can do that. Hang on just a minute. Okay, so I think if I did things correctly, I went out and started up Maple and then entered in the formula for the function that we're dealing with, x cubed minus 6x squared plus 5, and then just plotted it. And this is what it looks like. And from this graph, you can see where the absolute max is at 0, and the absolute min is at -3. So if we flip back to our work, that's what we have here. Our absolute min is at -3, and our absolute max is at 5. Now, we did that without drawing the picture at all, but we can verify, if we look at Maple, that that's what's going on in this particular example.